Thank you for the invitation. So I'm going to talk about actually our effort actually, as an example, try to convert this fundamental research in ultra-fast spin dynamics into potentially a device that's of ultra-fast spintronic devices. Okay, so what we did new here is two things I was saying is first we try to integrate this optical AOS material into magnetic tunnel junctions so that we create optically switchable tunnel junctions. Second is instead of tight sapphire lasers, we start to use infrared, very low cost fiber lasers working at the telecom wavelength range so that demonstrate the compatibility with telecommunication with Silicon Photonics. Hopefully that's a potential for large-scale integration with photonic systems. Okay? So the work I'm going to talk today is done when I was at University of Minnesota. Very recently, I moved to University of Washington. So the work is done by my former postdoc, Junyang Chen, former graduate student He Li, and collaborator Professor Jianping Wang. So the work is supported by this center, sponsored by DARPA and SRC. It's called the Center for Spintronics. It's about 30 PI consultant. The goal of the whole center is really to develop a spin-based computation system. Okay. So when we're talking about the advancement of a computation system, we immediately see this cliche you probably see in many places. So the problem in next generation computing system is while the processor or the computing power progress very fast, the I/O ratio, the input-output ratio, or the communication bandwidth on the chip or on your circuit board is lagging behind. Okay, so for example, the processor can go very fast, the memory getting bigger and bigger, but the communication between the two is limited. Right, the speed of that is limited. There seems to be a gap in there. To address that gap, right, then you need innovational technology. So the solution, well, of course, I should credit Professor Dan Miller from Stanford to use some of the graphs from his slides. So to address this interconnect problem, the solution seems to be an optical. So bringing a photonic interconnect onto the chip or onto the circuit board level, right? So it addresses several major bottlenecks. For example, in terms of energy, the electrical interconnect energy is getting too high, and the photonics has a potential to address that. And the further important is simply the physical density. So in your IC, you eventually physically run out of space for those pins to just driving data in and out as your data rate start to increase, because every pin can only carry that much data rate and you just need more pins. In reality, actually large amount, actually more than half of the pins on your chip is simply carrying the DC power to supply the transistor inside. Okay? So therefore, you will want a much larger so-called density. So basically, the channel, the communication density of the channel divided by the physical size of the channel. Okay? So therefore, optical interconnect has its advantage because not only single channel speed is very high, but you can do wavelength multiplexing. A single waveguide can support multiple channels. I believe the speakers after me will talk more details about how to address these challenges. All right, so to make optical interconnect compatible to electrical, the key, of course, is to lower the energy consumption. The big advantage of optical communication is it doesn't matter how far it travels, it consumes the same amount of energy. Essentially, if you don't have a loss in your optical fiber or waveguide, it consumes the same amount of energy to communicate, doesn't matter how long it goes. So therefore, the energy consumption per bit versus the interconnect distance is essentially flat, right? And the goal is to beat electrical. However, on the other side, electrical is almost linear because the longer distance, you have to charge larger capacitor to send a bit of 1 volt, right? So the whole community working is try to pushing the energy consumption optical interconnect down. So therefore, it becomes more and more competitive with electrical interconnect at a shorter distance. Okay. So to make an optical interconnect work, you essentially need 4 things, right? First, you need the light source, which is the laser. Second, you need the modulator to encode electrical signal into optical signal. Then you need a photodetector to convert electrical signal of optical signal back to electrical signal. And finally, you need the waveguide or optical fiber as the connection intermediate between the two. Okay? So these figures show the representative devices that are being developed in the photonics community to realize all of these. And the community actually moving very fast, going towards a large-scale integration. So I quote the number 50 to 100 gigabit per link. Maybe this number already been updated in recent years already. Okay. All right, so to make this optoelectronics photonic device work, we're essentially exploring these fundamental excitations inside materials, right? That is the photons and the charges. And in addition, we often encounter phonons, that is lattice vibration or thermal agitation inside the materials. On the last corner is a spin, is the magnetic devices. So for all of the devices I showed earlier, to make them work, essentially all of them using photon and the charge interaction. That is either electro-optical effect inside material or the photoelectric effect to detect those photons to generate electrical signals. If you try to, so therefore all those devices can be called opto-spintronic devices, right? Optoelectronic devices, okay? So if you connect the other interaction, you get a very busy plot like that. What we realize is a less explored side of interaction is the direct interaction between photons and the spins, right? That is this workshop is concerned about. So in fact, that this interaction between spin or magnetic materials and photon actually play a very important role in optical communication. That is the Faraday effect that leads to the optical isolators that are being used everywhere in fiber optical communications. To prevent simply just force the light to propagate in one direction and prevent any reflection that actually may interfere with your lasers. In other way, photon actually we heard many times in different material systems may have the inverse Faraday effect. So if we focus on photons, then if the photon and the electron interaction leads to optoelectronic devices, then we explore photon and the spin interaction may into opto-spintronic devices. Okay. So when we actually putting the proposal together for the centers of to develop a spin-based computation system, then we realize that's a big problem because if conventional electronics-based computers are using opto-interconnect, right, then spin-based computers should also use opto-interconnect. Otherwise, all the spin-based energy speed advantage will be lost due to the interconnect inefficiency. However, the whole interconnect is based on optoelectronics. So if you take those existing technology, you are forced to convert the spin into the electron, then to talk to the photon, and the other way around, right? So imagine that you have to receive the optical signal with a photodetector generate electrical current, and you have to convert that electrical current or voltage into a spin information. So therefore, if you want really the spin-based system to be efficient, at least in the proposal level, then you really need a direct conversion between spin and the photons, right? So if you can directly convert one photon into one spin state, and vice versa, then you could actually potentially fully utilize the optical interconnect, the energy and the bandwidth advantage of optical interconnect. And of course, spin system has many other problems. For example, the spin current does not diffuse very long, so you have also the problem of long-distance communication of the spins. And the speed has also a limitation to split the spin. That's why we are very excited to see, again, rising groups working in optical switching in gadolinium ion cobalt, right? So it shows that there is a holistically dependent switching of magnetic switching. So we thought that actually it provides a solution. It's a venue to directly convert the polarization, the circular polarization degree of photons into the spin state inside solid state materials, right? So this is initially this helicity dependent switching. We see that's a venue to achieve a at least direct photon to spin conversion. We don't have a real solution for spin backward to the photon conversion. That is actually a more difficult problem. Okay, so back in 2012, as we putting it together, we have this kind of a scheme, okay, to work with. So imagine that we actually could bring that optical switching material into a magnetic tunnel junction, which is becoming a building block device for all those spin-based technology. So if we can integrate onto that a waveguide, okay, and then then we have a two waveguide, And on the other end, in the input end, we have a switch, which is set by another magnetic tunnel junction. Okay? So if the magnetic tunnel junction in one state can turn the switch in one state, then light will either propagating from the lower path or the upper path. If it's a propagating of the lower path and using this polarization converter, it's a photonics tricks that we use on the chip, then you can generate a, say, left-hand circular polarized light. And that light pulse actually shine onto this tunnel junction, switch that magnetic material, therefore you set the magnetic junction into a different state. Therefore, you are able to convert the photon, at least in this case, the path integration or the path state, either the photon takes the upper path or lower path into the spin state encoded in this magnetic tunnel junction. Okay? So that is sort of a scheme to realize such a spin-to-optical interconnect. So then we try to reproduce the results by developing our own gadolinium ion cobalt film, right? So we are using a very busy sputtering system doing different materials, so that initially become very difficult to control the composition. So at least we actually were able to make it perpendicular magnetized, then we were able to image the domains. Then we run our laser. In this case, we use the fiber laser, 1.55 micron. So we run the laser across the one film with different repetition rate. We were able to see the domain being switched, right? Then, so that was a little bit exciting. Then we see if you run across, then we see there's a problem because the intersection area is not reset by the laser scan. So it's an irreversible optical switching. And so therefore, I mean, the material is really not optimized at the beginning. Okay? But yet we wanted to do some device demonstration of that. So we make a simple whole body device. And we measure the anomalous Hall resistance of this device as we scan the laser beam across the device. Okay? So this is the first one of the first efforts to try to electrically read out the optical switching inside this material. As you can see that the material is not ideal, so we will only be able to partially switch the material with multiple optical pulses, right? Then we cannot switch anymore, so we have to apply this green marked magnetic field. So we have to apply another opposite magnetic field to reset the film. Then we can switch backward again, then reset it, then backward again, then reset it. Okay? So sort of demonstrate, so the electrical readout of the device with an unideal material. So when we get more time on the sputtering system, we were able to more carefully optimize the material, right? So not that easy. But anyway, so we understand there's it's a composition near the room temperature compensation point. That's within this window, you will be able to optical switch with a single laser pulses, as shown by this switch dot across the domain. So then we make the similar device. We pattern the device into a disk. We put down non-magnetic electrodes to avoid any stray field by the surrounding film, right? Then we measure the anomalous Hall resistance again, and then we show that a single laser pulse can toggle this gallium ion cobalt disk into up and down magnetic states, right? So you have a very high repeatability.
Which laser they can use?
Just a 1.55 micron. Yeah. So what we understand is it's relevant to the wavelengths. It's just a heating effect, right? So it's a much low cost, not tensile fiber laser, and it breaks down often actually. So you can shoot a little video. If you look carefully, you can see this is a current microscope video. You can see the central region being turned on and off from the contrast with a reparation rate of 1 hertz. Okay. So then with that film, we were able to develop a magnetic tunnel junction. So the tunnel junction, the standard use a titanium seed layer, then use a cobalt palladium multi-layer as a fixed layer, right? Then use the MgO as a tunneling barrier. Then you use the gadolinium ion cobalt as a free layer, right? Then you cap that with the titanium. Well, because you have to shine laser onto the gadolinium ion cobalt layer, you cannot put a simple metal top contact because it's going to block the laser. So we have to use ITO as a top contact. It's a transparent electrodes on the top, right? So the work then you shine laser from the top, okay? Then this is the optical image of device. Then you can characterize the device, a tunnel junction, by sweeping the magnetic field. What you see that actually is the coercivity field of a cobalt platinum multilayers is lower than the gadolinium ion cobalt layers, right? So that if you sweep the magnetic field, the cobalt platinum multilayer becomes the free layer. It toggles, it switches, right? And then the MS you can see from the MS loop, and the gadolinium ion cobalt layer actually switch later. Then you measure the tunneling resistance of the device as you're sweeping the magnetic field. You see that this is a typical TMR, tunneling magnetoresistant behavior of a MTJ device. So sadly, that the tunneling resistance of this device is quite low. It's less than 1%, right? For many reasons, okay? First is we can't anneal the device really, because usually to have high TMR, up to 100%, 200%, people have to anneal the MGU layer to be really crystalline phase, right? Just afraid of oxidizing the gadolinium ion cobalt layer, we avoid the annealing structure. Second is suspect that gadolinium ion cobalt is not a good material for making a magnetic tunnel junction, given its low spin density and the low magnetic moments. Okay, but nevertheless, we have a visible TMR from this device. So next experiment is simple, just shine laser lights onto that, right? We measure the TMR at the system. At the same time, you actually can take a curve imaging between the two switch states. You sort of can see the contrast difference, right? And you measure the TM magnetoresistance every time you have a laser pulse comes in, okay? So the laser pulse duration is about half a picosecond. So you see that every time you toggle the tunneling magnetic resistance of the device high and low, high and low, so that you demonstrate the optical switching, right? So you can see that actually the signal is very noisy. It's to blame the low quality ITU we were using. The ITU give you very bad contact, actually, give you a lot of measurement noise. But nevertheless, another thing to compare is actually the magnetoresistance compared to the switching when you're sweeping a magnetic field. They agree really well in terms of the TMR ratio agrees very well. Absolute resistance changes a little bit because your different experiment when you put probe down, every time you measure different contact resistance. But that's the TMR ratio agrees with the magnetic field sweeping. That tells you that you're really completely switching the top contact of the gadolinium ion cobalt layers. Okay, so that's actually do the switching every 1 second with a repetition rate of 1 hertz, right? So the question is, as a device, or you imagine that using that as a receiver to receive a data signal, how fast you can repeat this back and forth and back and forth, right? So we try to demonstrate that. So the way we do it is we're sending a pulse increase. We're sending the pulse with a much higher repetition rate, and we pick 1 or 2 using acousto-optical pulse picker. Okay. So what happens is if you're sending 1 pulse in every time, you set and reset the devices, right? But if you let the 2 pulses in together with a tunable delay, the second pulse will reset the switch of the first pulse, right? But if the second pulse comes in too soon, then the 2 pulse, the gadolinium cobalt layer don't have enough time to cool down and to finish the switching. Then you may not be able to switch backward again. So this is what you see here. If you're sending 1 pulse, you switch every time. If you're sending 2 pulse with a delay of 1 microsecond, then you don't switch. That is because the second one resets the first one's switch, right? And you send in 3 pulses, the third one will switch it again. Then you repeat that with the 4 pulses, you'll reset that, okay? So at least this work tells you that you actually can repeat the switching by 1 megahertz speed, right? So 1 megahertz is not fast enough because according to the time resolved XMCD study, right? So that the system should recover to the equilibrium at least by the time of about 20-25 picosecond. So you should be able to switch that fast. Instead of 1 megahertz, you should expect to be able to switch on the order of 50 gigahertz, right? So that will be very compelling in terms of operation speed, right? So we try to do that instead of using a pulse picker. We split one pulse into 2 passes and change the delay, right? Change by a variable delay between the 2 pulses and then recombine them to the device. What we see is if we only use 1 pulse from one of the paths, we can always switch. If you use a second pulse from the other path, you can always switch. But when you combine the two with a delay about 100 picosecond, you don't see switch. You can even reduce the delay to be 20 picosecond. You don't see switch, right? But does that mean really that the second pulse delayed by 20 picosecond resets the switching of the first pulse? It's not clear, right? We shouldn't be fooled by that because it's very likely that the switching never happened in the first place, right? So to really tell that, you need a time result study to do, say, a curve probing in between the 2 pulses, right? To see what's happening in between that. But the material probably tells you should be able to do that fast, right? Our study, I mean, of course, ideally you would want to keep delaying the 2 pulses, right? Then, or tuning the closer, then I actually reduce the delay, so eventually the switching reoccurs. I think it just our system has some limitation. We couldn't do that in this experiment, okay? All right, so then, so if you put this optical switching, so we demonstrate optical switching using laser pulses as short as half a picosecond, right? And you put this into a big picture of all the magnetic tunnel junction that has been switched either by spin-torque transfer or spin Hall effect, right? So Alex Kimball and I was writing a review article. So we thought we'd do some data collecting of the literature and plotted in this plot as a switching energy versus the switching time, okay? And generally, using microspin picture, you will see that for STT or SHE switching of a magnetic tunnel junction, the critical current switching is always increases with a time constant, with a reducing time constant tau. So meaning that if you want to switch faster, you need a larger current. That leads to an energy penalty. When you actually try to switch fast, you actually cost more energy. But if you do the slow, then you actually also consume more energies, okay? So when you throw all this data point collected literature and on this graph, and you plot this equation, you just use a guide of I using either a characteristic time constant tau 0 on the order of 1 nanosecond and a static switching energy on the order of a few femtojoule. Then you see that, okay, so you indeed, most of the data, even they belong to very different material system, all kinds of device geometry, they are more or less full on this line. So if you do too slow, you're consuming too much energy. And you actually can go, when you go faster, you have energy penalty. But the sweet spot seems on the order of 1 nanosecond to 100 picosecond order, and that consumes about 100 femtojoule per switching energy, right? Putting the AOS work in our device, we actually, you consider the device size is about 10 micron by 10 micron, right? And you take the energy, the fluence of the laser power you send in, you calculate the energy it takes it's consumed about 5 nanojoules to switch on the order of half a picosecond, okay? So it falls on here. However, it should be straightforward to reduce the device size by 100. So there's no reason to use a 10 micron. You can easily make 100 nanometer at least device. So that the energy consumption will drop by 4 orders of magnitude to be expected, right? You actually can argue go even smaller. So the reason of this is actually deviated from this curve is actually, this is a very different mechanism, right? It's really a thermal non-equilibrium process actually destroys the thermodynamic system in a macroscopic thermodynamic system. So there's the potential that the optical switching has the speed, both the speed and energy benefit in terms of switching a magnetic tunnel junction device. Okay, so how to address the problem of our device with very low TMR? So this 1% TMR is not really useful. So one idea is really to introduce the right material for magnetic tunnel junction. For example, cobalt ion or cobalt ion boron layers, which is used for making high TMR magnetic tunnel junctions. And then you use the optical switchable layer, gallium ion cobalt layer, and allow them to exchange couple with each other. So switching the gadolinium ion cobalt layer with laser pulses, and then drive the switching of the coffee bean layer, which actually contribute to the high TMR ratio. Actually, back to 2002, this is a work from Japan. This is one of the first perpendicular magnetic tunnel junctions. If you look at the ZLD structure, they essentially already have that, right? So the gallium ion cobalt laser coffee bean layers, and although they were using amorphous alumina as the tunneling junction, but the structure is more or less the same. So you could actually replace this with the now high-quality crystalline MGU layers. Even with amorphous tunnel junction, you were able to demonstrate about 50%, more than 50% tunnel junction TMR ratios. So that seems to be a right route to go. Another thing is a reduced size. So we're already seeing the work from Stanford group using a plasmonic nano antenna. They demonstrate switching a domain size as small as about 50 nanometers. So if you be more aggressive, you may argue what's the ultimate energy consumption. If you have a 20 nanometer diameter MTJ, which has been demonstrated, and taking the energy consumption on the order of 1 millijoule per centimeter square, therefore you will scale down to 3 femtojoule per bit, right? So that in terms of energy also seems to be promising. All right, so let me talk a little bit about the photonics layer, because we wanted to do the conversion, generate the circular polarized light. So there's a lot of tricks you can do. Actually, Silicon Photonics integrated photonic devices is very powerful to manipulate light. So we developed this strategy. You can actually, using this beam splitter, in one of the paths, you're adding a phase shifter, tunable phase shifter. Then so that you actually introduce a phase delay of linear polarized light. Then you rotate by, physically rotate by 90 degrees and combine with the other unphase shifted beam in the middle of this grating coupler. That allow you to generate arbitrary polarization state of light coming out of the plane. Okay, so that was the initial idea to generate circular polarized light to switch if the switching was helicity dependent, right? So we actually did that while we are developing material. So we're using metal heater as a phase shifter, right? So then the two beams combine into this two-dimensional grating coupler, right? And you actually can see this red spot as an infrared emission coming out of this grating coupler. The beam has a beam width on the order of 2 micron. So the original plan was to integrate the gadolinium ion cobalt layer on top, then demonstrate switching on an integrated platform. Okay, so simply by applying heat to this heater, integrate on one arm of the waveguide, you are able to induce a phase shift, and then you actually change the polarization state. So this is a Stokes parameter of the light telling you the polarization state. So you actually generate code from linear to left-hand circular to right-hand circular to linear and so on. So allow you to do the gen. So even though we now understand that the switching is helicity independent, at least in gallium cobalt, this device platform actually going to play a big role in many quantum optics applications. Anyway, so that's our artistic envision of scaling up in this magnetic tunnel junction as a random access array. I see similar pictures. Seems your artist is better than my students' work, but the idea is the same. But of course, the biggest problem is addressing the size mismatch between a small magnetic tunnel junction and the diffraction limited laser beam, either coming out of a grating coupler or just coming from free space. Seems the the plasmonic near-field transducer is a solution. So I'm very excited to see Professor Bert Koopsman's work on this bilayer. So that actually makes the material development so much easier. So you don't have to fine-tune your sputtering system to tune the composition into the right, a very small window to make it work. You only need to tune the thickness of two clean layers to be able to achieve that. And the reset track idea is very attractive. And of course, to write a very small domain, you will result to the near-field plasmonic structures of that. Okay, so so I just like to advise one more work we did is a topological insulator. Since we heard a talk yesterday about circular polarization photogalvanic effect in topological insulators. If you shine circular polarized light on topological insulator, you actually generate spin polarized light. It turns out that the evanescent field of a waveguide is also circular polarized, but in the side way, pointing in the transverse direction. So in this work, we show that using this circular polarized evanescent field of waveguide, you actually also generate spin polarized photocurrent on the surface of topological insulator. More interestingly is this, because the light propagation in the time reversal symmetric, if you reverse the propagation in the opposite direction, the photon spin also reverses. So therefore, you generate optical spin opposite spin on the circular polarized light. Okay, so in matter of time, I'll just stop here and with acknowledging my student and postdoc who did this work. And thank you for your attention.